Last time we used row echelon form to find rank and nullity. Today we focus on the concept behind solving AX equals 0 and AX equals B. The row operations are not the star today. You have already seen them enough times. Everyone deserves mercy, including algebra. We use the same matrix A as last time. After row reduction, A becomes the echelon matrix U shown here. Because row reduction comes from invertible elementary matrices, AX equals 0 and UX equals 0 have the same solutions. First, AX equals 0 is exactly the problem of finding the null space of A. By definition, the null space of A is the set of all x in F4 such that AX equals 0. So solving AX equals 0 is not a separate topic. It is literally finding null A. These are the directions that A collapses to 0. A linear map's private shredder. If you like unpleasant office metaphors. Now solve AX equals 0 using the echelon form U. From the last row, x4 equals 0. Then the second row gives x3 equals 0. The first row gives x1 equals negative 2x2. So x2 is free, and every solution is x2 times the vector negative 2, 1, 0, 0. That means null A is the span of this one vector. This is the null space. Not just a random answer wearing parentheses. Now compare that with AX equals B. AX equals B asks for all inputs x that A sends to the target vector B. So AX equals 0 asks for the inputs landing at 0. AX equals B asks for inputs landing at B. Same machine, different target. The notation changed one letter and somehow caused generations of homework. Let us choose a concrete B and solve AX equals B. Take B to be 1, 3, 2. This B is the third column of A. So one particular solution is xp equals 0, 0, 1, 0, because A times that vector selects the third column. If we row reduce the augmented system, we get the same echelon matrix with a transformed right side. The row-reduced augmented system looks like this. It says x4 equals 0, x3 equals 1, and x1 equals negative 2x2. Now write the solution set on a cleaner screen. Because apparently formulas also need personal space. So the solutions are one particular solution plus x2 times the null space direction. The same vector from the homogeneous equation appears again. It was not unemployed. It was waiting. Now here is the main conceptual point. Suppose xp is one solution to ax equals b, and z is any solution to az equals 0. Then a of xp plus c equals axp plus az, which equals b plus 0. So every null space vector can be added to a particular solution. And we still have a solution to ax equals b. Translation. Once you find one solution, the null space tells you all the ways to move without changing the output. We also need to know that this gives all solutions, not just some pleasant-looking ones. If x is any solution and xp is one fixed particular solution, then both map to b. Subtract the two equations. A of x minus xp equals 0. So x minus xp lies in the null space. Therefore every solution is xp plus a null space vector. That is the full relationship. Particular solution plus null space. A suspiciously elegant sentence. So naturally we had to spend a whole video earning it. This also explains the possible shapes of the answer. If b is not in the range of a, then ax equals b has no solution. If there is a solution and the null space is only 0, then the solution is unique. If there is a solution and the null space has non-zero vectors, then there are infinitely many solutions. So the null space controls the freedom in the solution set. It is the source of the wiggle room, mathematically speaking, because apparently we needed a dignified term for that. Let us summarize before the symbols start pretending they were obvious the whole time. Solving AX equals 0 means finding null A. The null space contains exactly the directions that A sends to 0. If XP is one solution to AX equals B, then XP plus anything in null A is also a solution. And every solution to AX equals B has that form, particular solution plus homogeneous solutions. Next time, we can use row reduction as a practical recipe for solving these systems theory first. Button pushing second. Radical behavior.